Okay. Hello and welcome to my talk, Next Generation Mobile Rootkits. My name is Thomas Roth. I do embedded security, like hacking payment terminals. I do a bit of distributed computing and mainly breaking and web stuff. You can find me on the internet, on Twitter at Stack Smashing. And yeah, hope you enjoyed. So let's start with a short introduction into the world of mobile rootkits and ARM Trust Zone. So what are we protecting on a modern mobile phone? We have our communication. Doesn't matter if it's actually calling, if it's writing SMS or WhatsApp for some poor souls, or even if it's real-life communication, because if I can use your phone as a bug, that's a problem. We are protecting data, like a lot of people have documents on their phone from their businesses or presentations and so on. We are protecting credentials like VPN keys, or likely your email password is also the password you're using to log onto your network and so on. We have payment, like NFC payment with Google Wallet, with MasterCard and Visa's papers, and possession data, because if I can rootkit your mobile phone, I can track you. What kind of rootkits have we seen in the wild? There was the famous Carrier IQ, which was used for usage statistics officially, which interestingly didn't only hide in the CPU but also in the baseband for some vendors. Then there is FinFisher, or FinFisher Mobile, which is governmental surveillance. And there's Cloaker, which is a very interesting research paper about ARM rootkits. Where would I hide a rootkit on a mobile phone? I have actually two choices. There's the CPU, which on the desktop does everything that has to do with the operating system, everything that you actually see. And then there's the baseband. The baseband is the communication chip. It implements the 3G, it implements the actual calling and so on. And interestingly, on most hardware platforms, the baseband and the CPU both have full memory access. So if you can own the baseband, you own the device. In this talk, we are going to focus on a small hardware edition by ARM called Trust Zone. Trust Zone is basically a secure chip in your ARM processor, and yeah, it's quite interesting. Who of you has absolutely no idea of ARM processors, like coprocessors and so on? Okay, great, thanks. Yeah, then a short ARM intro. ARM is a 32-bit RISC architecture, RISC-reduced instruction set, so you have a small set of instructions that are simple but can be executed relatively fast. Yeah, 32-bit. On x86, your instructions can have different lengths. Like you can have, as we've seen earlier in the virtualization talk, 15-byte instruction. On ARM, all instructions are 32-bit long, except in the so-called sum mode, which is a mode for extra small instructions, normally only generated by a compiler, which are only 16-bit long. And there's some too, but that's a whole different story. On ARM, peripherals like IOs, like maybe your frame buffer, maybe some keys on your mobile phone are mapped into memory. So if you boot up your device and without setting up the memory protection or management unit, and you write at some addresses, maybe some LED lights up, or you can check whether a key is pressed and so on. Also, coprocessors play a very important role on ARM processors. A very famous one is the CP15 coprocessor, which is available on all modern ARM processors. It's called the system control coprocessor. You can do things like configure the MMU, configure power saving, set up your caches, set up where the TLB will reside, and so on and so on. So what about ARM Trust Zone? ARM Trust Zone basically allows the processor to switch into a secure mode in which it hopefully will only execute trusted instructions. The great thing about TrustZone compared to having a smart card or something similar in your mobile phone is that TrustZone can have access to the screen, to the keyboard, and so on. So you have secure input and secure output, which is normally considered a problem, because if you have a smart card in your phone and you enter the PIN just on the display in your Android app or whatever, in theory, malware could grab the PIN and talk to the smart card themselves. This is not the case with TrustZone because it runs on the CPU and can do everything itself. It officially protects against malware, trojans, and rootkits, and so-called trusted execution environments, which are basically small operating systems will run in it. And it's available since ARM v6 KZ, which is basically all modern ARM CPUs. Yeah, we will get to the irony of the rootkit thing later. Officially, the ARM TrustZone splits the CPU into two worlds. That's the official terminology. You have the secure world in which only trusted code runs, and you have the normal world in which your Windows Phone, your Android, your BlackBerry OS, or whatever will run. The communication between both worlds is via shared memory mapping. So if you want to have TrustZone do something, you put it into a memory area, go into TrustZone, and TrustZone will work on that memory and give back information via another shared mapping. Another cool thing is that the current CPU state is indicated to all peripherals on the internal buses of the CPU. So you can have like special memory that is only available in TrustZone. A lot of mobile phones do that with their integrated MMC card. So they have a partition that is only available in TrustZone. Trusted execution environments, as said, they are basically small operating systems providing services to the normal world, and you write small apps for them, like for instance your DRM driver, your movie encoder or whatever, and pay somebody. I try to find out who have to pay or to actually get an SDK or to be allowed to write such an app for the trusted execution environment, but nobody was able to give me an answer because I'm just a small company and so on. And if you have any idea what would be a good way to approach a vendor, please contact me. And you use them in your operating system via driver. For instance, on Samsung devices, you have /dev/tzic, which is a small TrustZone driver. And they are often open source. For instance, the official mobile core driver is open source. And if you take a look at it, you may find some interesting things. To give you a real-world example, in the USA, Netflix is very common, and they also wanted to go on mobile devices. Netflix is movie and TV show streaming, and if you want the low-quality videos on your device, you have to get certified by Netflix. For the low-quality videos, you just need to show, okay, our device is fast enough, and we can really stream video in real time. But for HD, the big movie labels require end-to-end DRM. So Netflix had to come up with something that ensures that no one is able to just screen grab the movie from the device. And what they do is basically they download chunks of the video, put it into TrustZone, and let TrustZone decrypt it and display it on the screen. So you can't just record the frame buffer on Android because it's rendered in TrustZone. Yeah. What does it protect against? Well, first off, TrustZone is not only about protecting the user, but it's mostly about protecting against the device owner in cases of DRM. Then it tries to protect against malware so that your credit card, your Google Wallet, and so on isn't easily stolen from the device. And in some cases, it protects against freedom, because even if you unlock your device and everything, the TrustZone code will still be there and you will have no idea what it does. It can do anything, for instance, be a rootkit. So how does it work? The The official documentation describes it as a second register set to the CPU core. So it's basically you switch into the secure world and it feels like your own ARM core, but actually you're sharing it with the normal world core. The mode switch from the normal world into the secure world can be either done by the so-called secure monitor call or by hardware exceptions. For instance, if a button is pressed or the NFC device is activated, the hardware can automatically switch into a secure world. There are also special interrupt controllers available for them. On the internal buses, there's the NS bit, which indicates the current secure state to all peripherals like screen and so on. So it looks basically like that. You have your normal world with all the privileged and user modes. You switch into the secure world, which is you switch first into a small monitor mode, a small code base. We will get into it later. And then into the secure world where you again have privileged modes and user modes. So if you write an app for a trusted execution environment, it can actually run like an application abstracted from the kernel and doesn't have all the rights that the kernel has. So how does it actually work? You only have this one CPU core, and you do a call into the monitor mode, which I call SMC mode here. And the SMC mode basically stores all current registers, turns on the NS bit, and then gives back the execution to the standard CPU, but this time with the enabled NS bit on the bus, and so it feels like it's actually two cores, but it's only one. Yeah. So the SMC mode basically has to detect, okay, is the current request coming from the normal world or the secure world? And depending on that, it either stores the the registers of the current world, loads registers of the new world, toggles the NS bit, and gives execution back. Memory in trust zone, as so you have the normal and the secure world, and you need a way to separate the memory areas so that your normal world can't just access the memory of the secure world. And that's why on trust zone enabled platforms you have the trust zone MMU, where you can configure that certain memory areas are only available to your secure world. Some are shared, for instance, only readable by the normal world or only writable by the normal world, or both. And yeah, then you have your normal world memory, and the secure world can access all of that. And yeah, I guess you see why it's handy to have that if you're writing a rootkit. Before we can come to the interesting stuff, we have to talk about the boot process, because companies like Samsung and so on invest a lot of money into securing the boot process of their devices. When you start up the device, you first have a very simple bootloader in the chip itself, in the read-only memory, which loads some basic hardware abstraction, and then does integrity verification of the second stage bootloader using crypto keys stored somewhere not available to normal code. Then the second stage bootloader gets loaded from flash, initializes the trust zone and the trust zone kernel, locks down the device, and then starts up the operating system. And it's very important for trust zone system to work that both these stages in the boot process are trusted. There are special trusted boot things available for ARM, and yeah, if you try to really unlock a modern device, you will see that they are quite good at it. And yeah, but as soon as one of the pieces in this chain is broken, trust zone is broken. And so you could then read out secret keys and so on. By the way, if you go to HTC or similar companies and unlock your bootloader, you are not actually unlocking your bootloader. They are unlocking the operating system loader for you. But all the stages we saw here, where the initialization of the trust zone takes place and so on, where the real bootloader resides, it's still all locked down. So yeah, you will stay out of trust zone, and your device will run in normal world forever. Let's talk about hardware support. It's basically on all modern CPUs, as it seems, including the Apple A processors. We're currently working with some Americans on finding out more about that. Yeah. So basically, the vendor installs a small operating system somewhere on the CPU where you can't control it, where you can't just stop it. It's not like a small, I don't know, task item which you can stop from the operating system, but it will stay there, and you have no idea what it does. And this small operating system can do everything, and third-party apps from untrusted vendors, from my side untrusted, are installed in it. What could possibly go wrong? We all know that they are going to write very secure code, right? So, yeah, let's talk about building an actual rootkit in Trust Zone. What? A super small rootkit that either runs in Trust Zone and now even entirely in the monitor mode, if you let out all the features. It's the first Trust Zone rootkit, and it's implemented entirely in assembler because, yeah, compilers are for losers. Yeah. Why would you do that? First off, it's fun. It's really interesting. You will learn a lot about ARM processors, a lot about what companies that implement such stuff do wrong and what they do right. Also, people weren't talking about Trust Zone. It felt like everyone knows it's there, but no one actually tries to find out what are they doing there, and do we really want Trust Zone on our devices? And can we use Trust Zone for our own purposes, like, I don't know, do our GPG mail or whatever there. And also, if we are talking about trusted computing, the trusted is not only about the user trusting the hardware, it's also about the vendor not trusting the user. And in some cases, it's a bit about stopping blob, because I'm not an open source fanatic when it comes to that, but I would like to at least be able to disable it. Right now, it's like you always have this blob there that does whatever, and I don't like that. Yeah, why is Trust Zone such a cool place? As said, the operating system can't find you. Once you are there, the operating system may knows that something is in Trust Zone, but it has no idea whether it's a DRM implementation, whether it's, I don't know, GPG mail or rootkit. Even bootloader level memory analysis can't find it, as long as what HTC gives you as the unlocked bootloader executes in the normal world. And often there are even special storage facilities that you can use to lock data and get it away somehow later on. And AMD is building it into their desktop processors. So if we get lucky, we can even rootkit desktop PCs using an ARM rootkit, which would be quite cool. The first problem I had when I wanted to try this out was, how do I test it? I don't really like only doing something in software, because it tends to be different to the real world. Like if you try it in QEMU, it will be different. So I tried to get a dev board. The Texas Instruments OMAP, they all have Trust Zone, but they have two versions. There's the HS, I guess it stands for a high security version, and the general purpose version. If you buy a Beagle board, everything runs in normal world. The Trust Zone is completely locked down, and you have no idea what happens there. And they are really good at locking it down. So you can't just exploit the boot ROM. It's quite difficult, as it seems. I haven't tried it myself yet, but yeah. Then there's software emulation. QEMU supports ARM, and there was a very good paper about software development for Trust Zone, and they actually built QEMU Trust Zone, which does a good job at emulating Trust Zone. And until, I think, 3 months ago, that was the only way for me to test and develop the whole thing. Till then, we found a hardware hack for certain devices, for certain class of devices to execute code in TrustZone, but it's a bit ugly because you have to soldier around with very, very small resistors and stuff. And also, I really wanted to do this. I wanted to hack into a trusted execution environment. The whole thing isn't released yet. The whole exploits for trusted execution environments and so on, they will be released later this year. So I will only give a small overview. The first step for getting to work on a real device was I wanted to hack into a trusted execution environment, because then I could prove that my idea works on real mobile phone and that it's a real problem and so on. And yeah, first step was getting a binary image of a trusted execution environment. Unfortunately, they are not open source. There's one open source, but it was actually open source. They just put it down, and yeah. Firmware updates for most Android devices are only signed but not encrypted. So you can just download, either drive-by download by sniffing, or download it from the vendor's hidden FTP servers. You can Google for them in URL FTP, and the vendor name is quite successful. And yeah, you can just download them from the net and try to split them apart, because they also contain your Android stuff, application stuff, and so on. The basic workflow for that is to disassemble the bootloader. Unfortunately, when you start to analyze a bootloader or something similar, it's not like a standard Windows executable which you load into IDER and it will automatically see, there's code, there's data, because it's not an executable file format. It's really just the instructions and the data mixed, and you have to find out like if the processor switches the state from 32-bit to 16-bit sump instructions and back, you have to find this all. And yeah, this is what it first looked like when I loaded it in and run some auto analysis. Is this a yellow? I guess this yellow stuff is, I have no idea what resides there, and the blue stuff are actual instructions. And this is after I was finished with it. This is a big image, and this is all the code. And yeah, if you boot up a device and it executes some code, it may configure as the MMU and the whole memory mapping stuff. You have to find out at which address is your bootloader actually running, at which address is your TrustZone code running. And if you are really unlucky, you will have to analyze a lot of coprocessor instructions by hand till you find out how it works. So then I started looking for runtime mitigations like address space, layout randomization, and co in the trusted execution environments. And I was really wondering whether they are very, very good implemented or just not there. And it turns out no address space layout randomization, no data execution prevention, ARCA NX-bit, executable heaps, stack data, everything. It's basically exploiting like it's 1999. Just as a suggestion, just as a tip, string copy is not as easy as it seems. If you use a string copy to copy a string from one buffer into another, and you give a destination size, and your source buffer is exactly as large as the destination size, string copy won't null terminate. Please use strill copy, which is a BSD string copy function, and also I do code reviews. So if you have problems with such stuff, hey. And yeah, they're still often pretty hard to exploit, but in this case it was very easy, because immediately after the source buffer came other buffer where I could put data in, and it was really easy to exploit. You'll find more about that later this year. So yeah, we now have three ways to actually test the rootkit, and it's quite awesome now. The first thing you have to think about is how will I get my rootkit to execute regularly? Because if I just put it into trust zone, it will be there, it will be in RAM, but how do I get the CPU to actually execute it in regular intervals? Because I can't just write an Android driver called rootkit schedule that toggles every 100 milliseconds or so. Yeah, so also the latency that is induced by the use of the rootkit must be very, very low so that you can't just analyze the latency between certain calls and see, oh yeah, it now takes like 1 milliseconds to do certain calls or do software interrupts. There's something happening there. Yeah. To make them more clear, if you, for instance, you can set up the interrupts to immediately jump into the secure world. So this is something I use. I use the standard software interrupts so that as soon as an interrupt occurs, the CPU changes into the secure mode. The monitor code gets executed, my rootkit gets executed for a small time, and then it switches back into the monitor code and back to the normal world. The part I marked in red here will be latency. You have to make all this as fast as possible. So if your rootkit is copying a lot of data to the integrated MMC, you may not want to do a 1 GB transfer at once on a software interrupt. People will notice. But luckily, ARM gives even some tips on how to invisibly run one's code in trust zone, because you can. They suggest that you obfuscate interrupt timing and try to make it a bit fuzzy so that you can't just measure whether the rootkit is executing or not. So even if your rootkit has nothing to do, you still want to waste time on a software interrupt so that it can't be determined whether the rootkit is doing something or not. You can use the performance counters to measure the time. The virtualization talk today, if you watched the video, had some similar analysis to find out whether you're running on a virtualized environment, and it's basically the same problem. Yeah. So I already talked about using interrupts to transfer the control to the secure mode. There are two kinds of interrupts on ARM. There's the FIQ, the fast interrupt, and then there's the normal slow interrupt. The fast interrupt can be locked down so that it can't be masked by the normal world. So if a fast interrupt occurs, it will always land in secure mode and it will always execute. Normal interrupts can be masked so that they don't interrupt. For instance, if I have a very time-sensitive part of code, I will disable all interrupts so that I can make sure that the code executes very fast. Then there's the external abort interrupts, like if you do an invalid memory access. You can't really use that to go into the secure world because you can't predict when they will happen. You don't know whether they will happen a lot or only sometimes and so on. You could override the interrupt vector. So if you decide that the normal world will handle all interrupts, you can just override the interrupt vector. The research rootkit cloaker does that very good. And there are even special trust zone interrupt controllers which could be used, but it's difficult to find documentation about them because every vendor may change something with the interface and so on. Yeah, to give a better picture about IQ interception, as soon my phone is works. As soon as a software interrupt occurs, the monitor saves the state of the normal world, executes a small slice of the rootkit, restores the state, and the real interrupt handler is called. And as said, this is what generates the latency, and where you have to be very, very, very fast. So yeah, after finding out all this scheduling stuff and testing it a lot to find out whether it really works, because there are some differences to keep it simply, but between the emulation and the real world. And yeah, the basic boot process starts with the setup of the secure world. This is, you basically fall out of the ROM bootloader into your own bootloader, and the first thing you have to do is set up memory. You will have to turn on the MMU, tell the MMU, hey, I'm TrustZone, give me this area, and make sure that the normal world can't access it, configure your stack, create a page table, and I would suggest if there's no trusted execution environment normally installed on your device, put the rootkit into an address space next to a hardware mapping or some other mapping, so that someone who tries to implement something will only think, oh, the documentation is wrong, the buffer of the device is actually larger or something similar. Yeah, the initialization, I tried to make my rootkit as enterprisey as possible, so you can actually install apps in my rootkit. And as the system boots, you will have to initialize the rootkit so that it can set up its memory, set up its virtual threads, configure a small system call facility. So I implemented a small facility with which you can store stuff on the integrated MMC and so on. And it loads modules if modules are configured. The scheduler is a timer-based slice scheduler. On the actual hardware, I use the external interrupt controller to make sure that my rootkit only executes for a very small time until it gets back. Yeah, and I store files in secure storage if available. This is quite difficult because finding out which part of the MMC or of the peripherals are actually only available in the secure world. Yeah, you won't find any documentation on that for normal mobile phones. The second step is setting up the monitor code, which will store the progression between the normal and the secure world and back. As said, it will store the register banks, turn on the NS bit, execute the rootkit scheduler code, restore the old register banks, and turn off the NS bit. Yeah, this is the actual assembler code. It's very, very easy to write monitor code. Here you just get the current state of the NS bit from the coprocessor 15. You test whether it's 0 or not, and depending on true or not, you will see whether you're coming from normal or from secure world. After that, you will have to store all register banks. This is an instruction on ARM which just stores the current registers R0 to R13. Oh, that code is faulty, whatever. To memory, and then you switch through all CPU modes and do the same for all CPU modes so that you won't overwrite anything, and vice versa if you are restoring them. An important thing to keep track of is cache and pipelining stuff, because if you do memory accesses in the secure world and they're still in cache and you switch back to normal world, the normal world might be able to retrieve the cache contents. Be sure to have your cache configuration right and use pipeline flushing instructions, because if you turn off the NS bit while being in the secure world, maybe some instructions of your secure code will still be in a pipeline and execute. Yeah, another thing is what I did for latency reduction is that for the whole storing register banks and so on, I use tightly coupled memory. That is memory that is very, very fast to access on the CPU, and that massively reduced the time I spent in the monitor mode when benchmarking, and as more time as I save there, as more time will I have to execute my rootkit. The next thing was that there's a secure configuration register in the coprocessor, which I use to set the IRQ to always jump into secure world. And you can actually tell the coprocessor to make sure that the normal world can't read the state of this register. So the normal world won't even know whether interrupts are jumping into the normal or in the secure world, which comes in quite handy for executing invisibly. The next step is the lockdown of the trust zone, which is basically disable the modification of certain bits on the coprocessor, set up the worlds, and disable the NS bits so that you run in the normal world. This is just a sample configuration. If you play with it, you can get the slides online, and yeah, it will help you a bit, I guess. Oh, and I decided you can disable that the normal world can mask, disable interrupts, but I decided to not do it because yeah, it will be suspicious if the hardware is not able to disable interrupts. Why would somebody do that? Also, depending on which hardware you're running on, you may need to configure some other peripherals. External storage may require special configuration to make sure that the normal world can't access certain partitions and so on. And there's a trust zone protection controller, which also does some dirty magic to make sure that you stay invisible. Yeah, and after that, you just start the normal operating system or operating system loader. So that the trust zone is configured, the operating system starts entirely unmodified. You don't need to touch anything, not even the operating system loader. You can actually boot U-boot after the whole configuration thing, and nothing to see here for the operating system. Yeah, real-world problems. I tried to do it on a certain device first, and I couldn't get it to work at all. I was sure that I was doing everything right setup-wise, and then I started reverse engineering their original trust zone code, and as it turns out, they actually do some complicated power management setup in trust zone. So I had to integrate the vendor blob into this image, and it was terrible. Yeah, it boots. What do we do now? We have an execution environment that is entirely separated from the normal OS. We have configured the CPU and all the peripherals to hide all traces of what we are doing, and we get control of the CPU regularly because software interrupts are used a lot by operating systems, and yeah. We can access all user data. It doesn't matter if it's the integrated SD card, if it's something else. We can manipulate the memory of everything. I actually use TrustZone to root some lockdown Android versions on certain devices so that I can take a look at what the Android is doing, what they are trying to hide. And we can communicate. And that's something I want to talk, yay. But communication is quite hard because as you can imagine, you can't just send it out by network because you're not running a network stack on TrustZone. Because if you were, then the normal operating system couldn't use the network anymore. It was quite difficult to find a solution for that. You can either talk to the baseband directly, like reset it hard and tell it to connect to UMTS and just send it out via UMTS, which at least for the normal person is very difficult to sniff. But it's really a pain in the ass to implement. There's also this suggestion by Cloaker. They talk directly to the network hardware, but the problem is, you will notice if your phone sends out data, if you have a good network administrator and so on. It's very suspicious and very easy to detect. So yeah, communication was quite difficult. What else can we do? There's quite some secret stuff available. Once you break into a running trusted execution environment, you will find interesting keys, you will find interesting papers data, and it's interesting, but I won't go into too much details here until everything is resolved. Yeah, how can we install it in the wild? We can use an Android app to exploit the API. We can have the vendor deliver it, like with Carrier IQ and so on, or by a firmware update. If you're a government organization, I would guess that vendors would sign your custom bootloader with special features for you, or you can use a baseband attack and do it from there. Yeah, I have to be a bit quick. Interoperability. Ports to new hardware are very easy to do because it's almost the same on all hardware platforms. So as soon as you get your code into TrustZone, everything is cool. And yeah, only some peripheral and memory stuff differs, and you may missing some chips which not have to be configured then. I also started binary patching a trusted execution environment to actually contain my rootkit, just for demonstration purposes. I'm not using it for work, it's just a fun experiment for me, so if your device gets owned, I'm not at fault. And yeah, there's an open source TE, which is quite interesting to look at, and I integrated my code into it, and I'm planning to release it open source later this year. Yeah, detection methods. As said, the main detection method would be latency, or if you're stupid at communicating. And the only way to avoid having a phone, having a blob in TrustZone is to use phones that don't have TrustZone, but good luck with finding any. Yeah, so thank you, and any questions? The slides are online, and yeah. Any questions? No? Good. Then thank you very much.